In this lecture, we will discuss continuous and discrete time signals. We can broadly classify signals into two types. The first one is continuous time signals and the second one is discrete time signals. We will start our discussion with continuous time signals. The signals which are specified for every value of time t are called as continuous time signals, and they are represented by small x inside the parenthesis small t, where small x is the dependent variable and small t is the independent variable. And you can see signal xt is single variable signal because we only have one variable, which is time t. Now I will take one very basic continuous time signal. Y-axis is always for function or signal, and here function or signal is xt. X-axis is always for independent variable, and independent variable is time t. So x-axis is for time t and this is minus t. And we have one signal which is having amplitude equal to a when time is equal to t0. Then this signal starts to decline like this and it becomes 0 at this point. It starts to decline on the other side of the y-axis also, and it becomes 0 at this point, and after this it remains 0 till infinity, and it remains 0 till minus infinity. So this is our continuous time signal. We are calling it continuous time signal because you can see this signal is defined or specified for every value of time t. You can find out this signal xt for every value of time t from minus infinity to plus infinity. Now we will discuss discrete time signals. The signals which are specified at discrete time intervals, or you can say discrete values of time, are called as discrete time signals. In short, we write discrete time signal as DTS, and in short we write continuous time signals as CTS. The representation of discrete time signal is small x inside the square bracket small n. This is small n is not time but it is integer. So this is the difference between representation of continuous time signal and discrete time signal. We have the square bracket in place of parenthesis and we have integer in place of time t. So dependent variable is x and independent variable is small n. Now we will plot the discrete time signal using the plot of continuous time signal, and as the definition of discrete time signal says, it is specified at discrete time intervals. It is not specified for every value of time t, but it is specified at discrete time intervals. Let's say the signal xt is specified at t0, it is equal to a, and it is also specified at t1, and this is the value of the signal. It is specified at t2, it is equal to 0. In the same way, it is specified here at t3 all the way to tn. Here it is specified at t minus 1, this is the value. It is specified at t minus 2, t minus 3 all the way to t minus n. So you can see the signal is not specified at every value of time t. If you want to find out signal xt between time t1 and time t0, you cannot find it because it is not defined. So we have plot of discrete time signal in which the signal is defined only at discrete intervals of time. We discretize the time axis. Y-axis is for x n. At t0 this signal is a. At t1 this is the value of signal. At t2 signal is 0. At t3 again it is 0. At t minus 1 this is the value of the signal. At t minus 2 signal is equal to 0. This is minus t. So this is the plot of discrete time signal, and time interval, the time interval delta t, which is equal to t1 minus t0, t2 minus t1, t3 minus t2, and so on, may or may not be same. If this time interval is same, this means t1 minus t0 is equal to t2 minus t1 is equal to t3 minus t2 equal to tn minus 1. If this is true, then we say the discrete time signal is uniformly sampled. When time interval is same, the signal is uniformly sampled, and when time interval is not same, the signal is non-uniformly sampled. Now we will discuss one very important thing, the existence of this integer. You can see the x-axis is for time, but how we got the integer as the independent variable? Let's consider the case of uniformly sampled signal. Because of this, delta t will remain same, and let's say delta t, the time interval, is equal to capital T, and when this happens, t1 minus t0 is equal to capital T. In the same way, t2 minus t1 is equal to capital T. tn minus 1 is also equal to capital T. And let's say t0 is equal to 0, and when this happens, we need to make t1 equal to t, so that t minus 0 is equal to t. Similarly, t2 will be 2t, t3 will be 3t, and tn will be nt. And when we are having t as the independent variable, we cannot write xn. We will have x inside the square parenthesis and t, and we cancel out t, so we have 0. Here we'll have 1, we will have 2, we will have 3, all the way to n. So this axis is now for integer n, and from this representation also we will remove t. So y-axis is for xn and x-axis is for n, and we have the integer values like 0, 1, 2, 3 and so on. I hope you now understand why we have integer in case of discrete time signal as the independent variable. So this is all for discrete time signals and continuous time signals. Let's solve one example based on discrete time signal. In this example, plot of discrete time signal is given, and using this example I will explain one more way to represent the discrete time signals. First thing we have to do is to write this small x. Inside the curly braces we will write a small n equal to curly braces open, curly braces close, and the values which will come inside these two curly braces will be the amplitude. We have amplitude equal to 1, 0, 1, 2, 2, 1, and we will start from the leftmost amplitude and end at rightmost amplitude. So we have 1, 0, 1, 2, 2, 1. These are the amplitudes, but this information is incomplete because we don't have any information about the independent variable n. All these are the values of signal xn, and there is no information about the integer n. If I ask you to plot the discrete time signal using this information, you cannot plot it correctly. You know the amplitudes 1, 0, 1, 2, 2, 1 are the amplitudes of the signal, but you don't know at what n 1 is the amplitude of the signal, at what n 0 is the amplitude of the signal. And if you take it randomly, for example, you take 1 as the amplitude of the signal at -3, but 1 is the amplitude of the signal at -2, and once you take it at -3, automatically you will take all the other amplitudes at a wrong value of a small n. 0 will become amplitude at -2, 1 will become amplitude at -1, 2 will become amplitude at 0, this 2 at 1, and this 1 at 2. So you can see the whole plot is now shifted to the left by one place, and to plot it correctly we need to add information about the integer n. So let's see how we add the information about the integer n. We simply put one arrow right below the amplitude of xn when n is equal to 0. When n is equal to 0, amplitude of xn is equal to 1, so we will put one arrow right below this 1, and this arrow indicates value of xn when n is equal to 0. Now using this information we can easily plot the correct signal. When 1 is having the arrow below it, this means this is the value of xn at n equal to 0, and this automatically makes 2 as the value of xn when n is equal to 1, this 2 when n is equal to 2, and this 1 when n is equal to 3, and this 0 is the value of xn when n is equal to minus 1, and this 1 is the value of xn when n is equal to minus 2. So this is the correct information, and I hope this example is clear to you. If you have any doubt, you may ask in the comment section. I will end this lecture here. See you in the next one.